In this section, we'll be taking a look at the class of service concepts objective of the JNCIP SP exam. We'll cover an overview of class of service, traffic classification, traffic policing and shaping, scheduling, and weighted random early detection, or RED. For more detailed coverage of this topic, please check out the Juniper courses AJSPR, JL2V, and JL3V.
In this and in coming videos, we're going to take a look at class of service. First and foremost, what is class of service? Well, it's a way to look at traffic and to split that traffic into different groups, and then to give those different groups differential servicing within the network. Why do we want to do this? Well, not all types of traffic that are handled by a network are equal. Take voice, for example. Voice is very sensitive to latency. So if at all possible, we want to ensure a low latency path through our network for voice traffic. Also, think what happens on interfaces during congestion. With no differentiation between traffic, we drop all traffic equally. But within a network, some traffic is going to be higher value than others. And so if there is congestion, we want to be dropping the commodity traffic in preference to the more high value traffic that we ensure gets passed through the network without being subject to any packet loss. So that is class of service. How is class of service implemented on a Juniper device? On the right-hand side of the board here, we have an outline of some of the key elements of class of service on a Juniper device. And we can follow them through a packet arriving on a router, being processed, and leaving that router. On the top here, we have the flow of traffic on ingress. So this is as a packet is first received on a Juniper interface, how it's processed through the device. The packet will be passed from ingress line card to egress line card via the fabric. And then we can see the processing on egress, on the egress forwarding plane out until the final point where the packet is released from that Juniper device and passed downstream. So let's take a look at some of these key elements that participate in the Juniper class of service system now. We'll talk through them at a high level here, and in subsequent videos we'll delve into them in more detail. So traffic arrives on a Juniper router. The first thing that we need to do is we need to classify that traffic. We need to group that traffic into a group that's going to have common forwarding dynamics, what's called per hop behavior. And we do this with classification. We can either use behavior aggregate classification or multi-field classification. With that traffic classified, we then set some internal labels. They are forwarding class and packet loss priority. Forwarding class you can think of as loosely equivalent to a queue, and it's going to determine the traffic servicing on the egress interface. Packet loss priority, as the name suggests, indicates the likelihood of whether this packet should be dropped when we start to experience congestion, again on the egress side of processing. So we've set our forwarding class and packet loss priority via classification. What happens next? Well, we can use ingress policers to rate limit that traffic, and these ingress policers can reference the set forwarding class and packet loss priority. They can also set the forwarding class and packet loss priority if certain traffic gets above a particular level. Next comes forwarding policy. And if we so desired, we can use forwarding class to have differentiated routing within a device. Then, as I've mentioned, the packet flows to the egress interface. On the egress interface, we can be policing, we can be rate limiting that traffic again. On the egress interface, we can also be reclassifying using multi-field classifiers, should we so desire. And then On the egress interface, we can also be queuing the traffic. So we can be shaping the traffic, we can be scheduling the traffic based on forwarding class, or we can use weighted random early detection to start to drop traffic before a interface is congested, before tail drop starts to occur. And the final action is that we can rewrite some of the marking in the packet so that that marking can be read downstream. So we're affecting how traffic is classified on downstream devices. So that was an overview of class of service and some of the key class of service components on Juniper devices. In this video, we're going to take a look at traffic classification and rewrite. So we've said that we want to identify different groups of traffic and give those different groups of traffic differential servicing on a particular device. Classification is the means by which we identify what traffic should belong to a given group. And there are two main types of traffic classification: behavior aggregate and multi-field. So let's start off with multi-field classification. As the name would suggest, it means that we can look in more than one field to identify traffic. And we apply multi-field classification using a firewall filter that's applied either on ingress interface or egress interface. And we can use any of the from actions that we would typically find in a firewall filter. So we can essentially use any header within the layer 3 portion or the layer 4 portion of a packet to identify what type of traffic this packet is going to belong to. And so this gives us great granularity in how we can identify traffic. And what we then do is, within that firewall filter, we then set, using a then action, the forwarding class and maybe the packet loss priority as well. And so this is the first main way that we can classify traffic. Because we're looking at a large amount of the packets to do this, you can see that in the forwarding plane, the lookups that we need to do to be able to analyze all of these different fields can be resource intensive. And this could be particularly sensitive on a core device that's handling huge volumes of traffic. So is there a way that we can simplify the classification downstream? Can we maybe perform multi-field classification at select points in the network and then use a more simplified form of classification downstream? We can absolutely do that, and this is the standard design for quality of service in most networks. It also means that configuration downstream can be simplified. You're not having to deploy large volumes of firewall filters on downstream devices, for example. And so let's walk through how this operates. So what you would typically do is that you would deploy these multi-field classifiers around the edge of your network, forming what's called a boundary of trust. And you would identify traffic using things like source and destination IP address, source and destination layer 4 port, incoming interface, things like that. And using those criteria, you would assign a forwarding class, a packet loss priority. And that traffic would then flow through the Juniper device. Then, as the traffic is pushed out of the egress interface to downstream devices, we perform what's called traffic rewrite using rewrite rules. And using rewrite rules, we set certain values within the packet, within the frame, and those values can then be used by behavior aggregate classifiers on downstream devices to set the forwarding class and the packet loss priority. And there are only a small number of values that we are setting that behavior aggregate classifiers are analyzing. So this is much less resource intensive in the forwarding plane, so is much better suited to core devices that are passing large volumes of traffic. What fields can we set that can be used by behavior aggregate classifiers? Well, the fields that we use vary depending on the packet, the frame type. If we were pushing Ethernet frames, we would use the 802.1p header that's included with VLAN tagging on Ethernet frames. And that could be one of 8 values. We could be setting the experimental bit in MPLS frames. And again, this could be one of 8 values. And in IP packets, we could be setting either IP precedence or DSCP. These values consume the same portion of the IP packet header. It's just that DSCP is a more modern framework and it's using slightly more of the packets to perform that classification. And with these values set, with the EXP bit set, with a 802.1p value set, with a DSCP value set, packets are passed downstream, and say this is now a core router. The core router uses a behavior aggregate classifier, analyzes, say, the EXP bit, and then sets the forwarding class and the packet loss priority accordingly. As you can see here, we first look at the behavior aggregate classifier and then the multi-field classifier. Therefore, if we have behavior aggregate values set in a packet that's received, and we classify based on that, but we also have a firewall filter performing multi-field classification, the multi-field classification overrides the behavior aggregate classification. And in this video, we took a look at traffic classification and rewrite. In this video, we're going to talk about policing and shaping. So you can see on the diagram that we can apply policers in several locations, and then we have shapers applied separately as well. Let's first talk about what we're going to be achieving with policers, both on ingress and egress. So with policers, we can be doing one of 2 things. We can be actually rate limiting traffic, and we do this using a single rate dual color policer. What we're saying is we're assigning a committed information rate, a rate above which traffic shouldn't cross, and we have a committed burst size. So we have a tiny amount of extra burst above that committed information rate that we're allowing. And then any traffic that goes above the CIR and consumes the committed burst size, we're then dropping on the floor. And this is the primary use of policers. And we can be doing this both on ingress and egress. There is a secondary use of policers, and what we can be doing with policers is that we can be marking certain types of traffic differently depending on the offered rate of that traffic. And we can do that with a single rate dual color policer. So instead of dropping that traffic on the floor now, we're changing the marking. Maybe we're changing the packet loss priority, for example. This is what's called soft policing. We're identifying traffic for differential servicing downstream. When we're dropping traffic on the floor, that's hard policing. And we can do both with a single rate dual color policer. There are 2 other types of policer that we can use, and they are the single rate tricolor policer and the dual rate tricolor policer. And both of these can only be used for soft policing, i.e. for changing marking like packet loss priority. And with both of these tricolor policers, as the name would suggest, we can have the base level of traffic and then that we just don't do anything to. That's one color. And then we can have 2 other colors. So we can have 2 other markings depending on the offered rate. You know, if the offered rate increases slightly, we mark one type of packet loss priority. If it increases beyond a further threshold, we then mark a different packet loss priority again. And then these markings would be used downstream for differential treatment of this traffic. It's a key thing to note here about the order of processing between firewall filters and policers. It's different depending on whether we're talking about ingress interfaces and egress interfaces. Firewall filters are processed first on ingress, and then we expose any polices that are configured. And on egress, the order is reversed. We police first, and then expose firewall filters. So that was polices. Let's now finish off by talking about shapers. With traffic shapers, we are limiting the rate of traffic that we are sending, much like we are with policers. But shapers address one big deficiency of policers. So if you have a policer and you're rate limiting traffic, what happens when that traffic is rate limited is that we're dropping a load of the traffic on the floor. This is likely going to include TCP traffic, and this drop of traffic means that the TCP sender is going to enter congestion avoidance. He's going to reduce the sending window, and the offered amount of traffic is going to decrease. We never actually get traffic hitting the configured policing rate because of this continual back off of TCP senders. And to address this deficiency, shapers act on traffic differently. They are trying to achieve the same thing. They are rate limiting traffic. However, any traffic that's bursting above the configured rate to a certain point is buffered, and that buffered traffic is then smoothed. So if you have small bursts of traffic for a short period of time, that traffic is captured by the buffer of the shaper, and then it can be offered when the traffic level reduces. This has the net effect that we are exposing TCP senders to less packet loss. So we're having less congestion avoidance with TCP, so that we end up getting a rate much closer to the configured amount that we're shaping at than if we were using a policer that we were policing at. And in this video, we talked about traffic shapers and policers. In this video, we're going to take a look at scheduling. So this is where we actually get to the point on the egress interface where we're going to be differentially servicing different types of traffic. So it can be sending some traffic in preference to other traffic. And it's best walking through this relating to the actual configuration that we have on Juniper devices. So we have our forwarding classes, and traffic has been classified accordingly into those forwarding classes. Via a scheduler map, we then associate forwarding classes with schedulers. And schedulers have a few bits of configuration. The first bit of configuration is priority. So we're saying what priority we want to assign this traffic, how quickly we want to get this traffic out of the egress interface. And Juniper devices use a modified weighted round robin algorithm. So what we're going to be doing is we're going to be servicing high priority traffic above medium high, above medium low, above low. So as long as we have some high priority traffic, we're going to be servicing that. We're going to be sending that out of the interface before we send out medium high, and so on down the stack. This is true as long as this traffic is said to be in profile. So there's a second configuration parameter, transmit rate, that we're assigning to a scheduler along with priority. And this transmit rate could be an absolute rate, so 100 megs. It could be a percentage of the interface bandwidth. And as long as a particular forwarding class is operating below that transmit rate, it's said to be in profile. So say we have video traffic, and we've assigned this video traffic to a video forwarding class. And this video forwarding class is pushing 200 megs of traffic out of the egress interface. That forwarding class is associated with a scheduler that has a 300 meg transmit rate. All of that video traffic is considered to be in profile. Now say that video traffic increases to 400 megs. The 100 megs above the 300 meg transmit rate is said to be out of profile. And we're going to be servicing out of profile traffic beneath in profile traffic. So say this video was high priority, we're going to be servicing that 100 megs of out of profile traffic lower than even low priority traffic that's operating in profile. This way, we can ensure that no one type of traffic is starving other types of traffic for service if we design our class of service scheme appropriately. There is one exception to this, and that is the strict high priority. There's no concept of out of profile traffic when it comes to strict high. And another final thing to bear in mind is that this is the software configuration of class of service scheduling on Juniper devices. How this configuration actually maps to the hardware implementation of schedulers is platform dependent. So you need to consult your platform specific guide if you need to know the exact details of how this scheduling is actually implemented using hardware queues and hardware scheduling on specific platforms. In this video, we're going to talk about RED, or Weighted Random Early Detection. And RED is in existence to solve two main deficiencies. So let's talk about these deficiencies in relation to how a egress interface processes traffic when that egress interface is congested under normal conditions where we don't have RED applied. So we have traffic passing through our Juniper device, reaching the egress interface, and there is more traffic arriving on this egress interface than this interface can service. So the first thing that happens is that the buffer associated with this egress interface fills up. The next thing that happens is that when there's no more buffer there, packets are dropped. We are subject to what's called tail drop. And there are two main deficiencies, as I've said, with this behavior. The first is that we're dropping all packets equally. We're not differentiating between different traffic types. And as this was one of the main goals of class of service, we're failing that behavior here. And the second is that we are exposed to TCP global synchronization. So as we drop packets here, packets are dropped in all TCP flows that are routing across this interface. And this packet loss in all of these TCP flows causes the TCP algorithm of the sending devices to undergo congestion avoidance. So that means that the TCP windows are reduced, so that the senders start to send traffic at a slower rate. So this has the effect that the amount of traffic flowing over this interface decreases, and it drops below the sending rate of the interface. So we clear our buffers, we're in good health again. Some time passes. These TCP senders now start to ramp up their window size again, start to ramp up the amount of traffic they're sending. And after a period of time, we then start to hit the transmit rate of this interface, we fill our buffers, we start to tail drop. So we have this continual oscillation between running at line rate, packet loss, dropping, line rate, packet loss, dropping. And this is obviously undesirable. We're not getting the maximum amount of traffic through this interface that we could, and all of the TCP senders on this interface are experiencing negative behavior. So we turn to RED to address these two limitations. So what we do with RED is that we have a fill level of the queue, and we have a drop probability. And we assign these two values with drop profiles to forwarding classes. So now that we can treat different types of traffic differently, we can drop some traffic in preference over other traffic by giving commodity traffic a higher drop probability than, say, more important traffic. And what happens here is that instead of waiting until the buffer completely fills, we're waiting now for the buffer to hit the fill level associated with that drop profile. And when it does, we then drop the percentage of traffic that's assigned to that drop probability. Say we have a 50% drop probability at 50% queue depth. So as the queue reaches 50%, traffic associated with that drop profile now has a 50% chance of being dropped. And as the queue fills further, that percentage value can increase further, so we start to drop more traffic. So as I've said, because we're assigning different drop profiles to different forwarding classes, this is what gives us the differentiation of service. How this addresses the second issue of TCP global synchronization is it means that we are not affecting all TCP sessions flowing across our interface at the same time. We're only affecting a subset of them, a percentage of them relating to the depth of the queue. Thereby, we're only causing a subset of the TCP sessions to undergo congestion avoidance and to window down. So hopefully now this means that we're going to get a nice fill of the interface, and it's going to stay relatively stable rather than being exposed to that permanent oscillation of traffic levels. And in this video we talked about RED, or weighted random early detection.